So this is the review for the first exam, and I'm going to go over all the problems in order. So problem 1 is to find two limits. The limit x cubed plus 1 over x squared plus 1 as x goes to 1. Well, as x goes to 1, x cubed and x squared both go to 1. So this is 1 plus 1 over 1, or 2 over 2, or 1. So that's pretty straightforward. B, as x goes to infinity, we have a rational function, 8x to the fourth minus 3x squared plus 11 over 5x to the fourth plus 1. And we know that when you have a rational function, if the numerator and denominator have the same degree, and in this case they both have degree 4, the limit is just the ratio, the quotient of their leading coefficients, 8 over 5. That's all there is to it. When we have the limit as x goes to infinity of sine of 3 theta over 2 theta, what we have to remember is that the limit of sine theta over theta as theta goes to 0 is 1. And so the limit of sine 3 theta over 3 theta as theta goes to 0 is also 1. But here we don't have sine of 3 theta over 3 theta, it's 2 theta over 2 theta. But we can certainly write this as the sine of 3 theta over 2 theta. But if I multiply the numerator and the denominator by 3, that's certainly legitimate. This is like 3 halves sine 3 theta over 3 theta. So that's 3 halves times the limit as theta goes to 0 of sine of 3 theta over 3 theta. And that's 3 halves times 1, or 3 halves. And that's the answer. D.
Why did you put theta goes to 0? It was x goes to...
Yeah, theta goes to 0. Thank you. And then D is the limit as theta goes to 0 of t times the cotangent of t. So again, you have to remember the definition of the cotangent is the cosine over the sine. So this is the limit as there's a typo. This should be a t. T goes to 0, t cotangent t. Limit as t goes to 0 of t cosine t over sine t. If you like, you can think of this as the limit as t goes to 0 of the cosine of t over, so t over sine t is like 1 over sine t over t. And as t goes to 0, the cosine goes to 1, and sine t over t goes to 1, so the limit is 1. Okay, that's problem number 1. Problem 2, we have the function which is defined as follows. F of t is equal to f of x, 3 times the absolute value of x over x. If x is different from 0, this is not defined when x equals 0, but it's defined to be 1 if x equals 0. So for example, f of 1 is 3 times the absolute value of 1 over 1, which is 3 times 1 over 1 is 3. F of 0, we're told, is 1. And f of minus 1 is 3 times the absolute value of -1 over -1. Absolute value of -1 is 1, so this is 3 over -1, or -3. And in fact, if we graph this function, if x is greater than 0, f of x, which is 3 times the absolute value of x over x, if x is positive, absolute value of x is x. And the x's cancel, and this is 3. So for x positive, it's this horizontal line. If x is negative, 3 times the absolute value of x over x. If x is negative, the absolute value of x is minus x. So this is 3 times minus x over x, which is -3. And when x is equal to 0 again, the value of the function is 1. So, and if you look at the graph around x equal 1, f of x is continuous at x equal 1. But if you look at the function at 0, as you approach 0 from the right, the limit is 3. As you approach 0 from the left, the limit is -3. So f of x is not continuous at x equals 0. What about problem 3? In problem 3, we have the function f of x, which again is equal to 1 over x squared for x different from 0, and we're setting it equal to 1 when x equals 0. So f of 1 is 1 over 1 squared, which is 1 over 1 is 1. F of 0, we're told, is 1. And f of -1 is 1 over -1 squared, which is 1 over 1, which is also 1. And if we graph this function, 1 over x squared is always positive. The graph of 1 over x squared looks like this. And it's set to be equal to 1 at 0. So here's the point 1, 1. This function is continuous at x equal to 1, because as you approach 1 from the right or the left, the function value approaches 1. But as you approach 0 from the right or the left, the function goes to infinity. The limit doesn't exist at all. So f of x is not continuous at x equals 0. Problem 4 is a function that looks very similar. Let's just see. Problem 4, we have the function f of x, which is equal to 1 over x squared for x different from 0, and 1 if x equals 0. Sorry, 1 over x squared plus 1. That's defined for all x, so we don't need to look at special cases. So in problem 4, the function is 1 over x squared plus 1. F of 1 is 1 over 1 squared plus 1, which is a half. F of 0 is 1 over 0 squared plus 1, which is 1. And f of -1 is 1 over -1 squared plus 1, which is also a half. And what does the graph of this function look like? Again, it's always positive. When x equals 0, it has the value 1. At 1 and -1, it has the value of half. The graph of this function looks like that. It's a very nice, smooth curve. It's continuous everywhere. F of x is continuous at x equal 1 and at x equals 0. The limit of this function of f of x as x approaches 0 is 1 from the right or the left. And that's the value of the function. So this is a function which is everywhere continuous. Problem 5 is to differentiate a series of functions. If you have f of x equal to the polynomial x to the 10th minus 11x to the 5th minus 3x to the 4th minus 2x squared plus 17, we're always using the fact that the derivative of x to the n with respect to x is nx to the n minus 1. If we differentiate this term by term, the derivative of x to the 10 is 10x to the 9. Minus 11 times the derivative of x to the 5, which is 5x to the 4th. Minus 3 times the derivative of x to the 4th, which is 4x cubed. Minus 2 times the derivative of x squared, which is 2x, plus the derivative of a constant, which is 0. So this is 10x to the 9th minus 55x to the 4th minus 12x cubed minus 4x. That's the derivative. In part B, we have the function f of x equals x to the 100th, x to the 1000th times the cosine of x. And for this, we have to remember the product rule for derivatives, which says that if you have a product of two functions, f of x, g of x, we're differentiating the product. That's the product of the first times the second plus the first times the derivative of the second. So here, this is the first function. Here's the second function. So for this function, f prime of x is the derivative of x to the 1000. That's 1000x to the 999 times the cosine of x plus x to the 1000 times the derivative of the cosine, which is minus the sine of x. So this is 1000x to the 999 cosine x minus x to the 1000 sine of x. That's the answer. In part C, we have a function g of x, which is the quotient of two polynomials, x cubed minus 1 over x cubed plus 1. And for this, we have to use the quotient rule, which says that if you have a quotient of two functions, f of x divided by g of x, the derivative of the quotient is also going to be a quotient. The denominator is the square of the denominator of your function. So this is g of x squared. And in the numerator, you get f prime of x, g of x, minus f of x, g prime of x. So here, this is my numerator. So this is going to be, let me put this in a, it's going to be the denominator. So this is my function. When I differentiate it, the denominator is going to be this x cubed plus 1 squared, denominator squared. The derivative of the numerator, that's 3x squared times the denominator minus the numerator times the derivative of the denominator, which is 3x squared. Let's see, I notice I get 3x to the fifth and minus 3x to the fifth, and 3x squared minus 3x squared. So the answer is 6x squared over x cubed plus 1 squared. That's using the quotient rule. Problem 5D. Well, we have a series of problems involving trig and exponential functions. So r of t is the tangent of t. To differentiate it, it's easy to remember that the tangent, by definition, is sine t over cosine t. So this is, again, a quotient. R prime of t, you take the denominator and you square it. And on top, you have the derivative of the sine, which is the cosine, times the denominator, minus the numerator, times the derivative of the denominator. Derivative of the cosine is minus the sine. So what we have here is cosine squared t, minus times minus is plus, sine squared t over cosine squared t. But cosine squared plus sine squared of any angle is 1. So this is 1 over the cosine squared, or 1 over cosine t squared, and 1 over the cosine is the secant. So we have the important rule that the derivative of the tangent is the secant squared. And what is the derivative of the secant? If r of t is secant of t, the secant is, again, 1 over the cosine. So we can do this if we like. We can use the quotient rule. So r prime of t, you have the denominator squared, and then on top you have the derivative of 1, which is 0 times the cosine, minus 1 times the derivative of the cosine, which is minus the sine. So you get 0 plus sine t over cosine squared t. And you can always write cosine squared as cosine times cosine. So this is usually written as the tangent of t times the secant of t. So the derivative of the secant is tangent times secant. F, we have a product of two functions. R of t is e to the t times the tangent. And the very important differentiation rule for the exponential function is the derivative of e to the t is e to the t. The exponential function is the unique function whose derivative is equal to itself. So by the product rule, r prime of t is, let me just write it out in 2 steps. It's the derivative of e to the t times the tangent plus e to the t times the derivative of the tangent. So this is e to the t, because the derivative of e to the t is e to the t times the tangent, plus e to the t, and we already computed the derivative of the tangent is secant squared. So that's perfectly good as an answer. F has to be followed by G. G is just another example using the quotient rule. Right? I mean, there are a lot of examples of problems involving differentiation because the minimum requirement you take away from Math 175. It's not enough, but a minimum requirement is you can differentiate any function. So in the G, we have the function f of x, which is sine x over x. So f prime of x, we have x squared in the denominator, because you square that, is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, but the derivative of x is 1. So that's the answer. Now, in problem 8, we use the chain rule. So this is in the first lesson for tomorrow, but the exam covers everything according to the syllabus, so includes the product rule, the quotient rule, and the chain rule. This says if you have a composite function f composed with g of x, and you differentiate it, you get the derivative of f evaluated at g of x times g prime of x. So this is the rule for differentiating a composite function. So in H, we have the function f of x equals sine of x plus 1 to the 7th. Maybe just so I can use the same formula, I'll just change this to H. Call it H. So H of x is sine of x plus 1. This is a composite function. If you had the function, let's say u equals some function of x, sine of x plus 1, and if we had a function y is some function of u, and say u is u to the 7th, then f composed with g of x, this is f of g of x. This is f of sine of x plus 1, and f raises everything to the 7th power. This is sine of x plus 1 to the power 7. So this function is a composite function for these two functions f and g. So by the chain rule, h prime of x, which is the derivative of f composed with g of x. Let me just write down these formulas. This is f prime of g of x, g prime of x. If f of u is u to the 7th, f prime of u is 7u to the 6th. And if g of x is sine x plus 1, g prime of x is cosine x. So h prime of x is equal to f prime 7 times g of x to the 6th times g prime of x times cosine x. So that's equal to 7. What is g of x? Sine x plus 1 to the 6th times the cosine of x. So this is an important instance of the use of the chain rule. Part I, we have the function h of t is equal to the natural log of t squared. So you could think of this as a composite function, the log of t squared, and use the chain rule, but it's simpler if you just remember the property of the logarithms. The log of t to a power is the power times log t. So the log of t squared is 2 log t. And one of the basic differentiation rules is that the derivative of log x with respect to x is 1 over x. The derivative of e to the x is e to the x. The derivative of log x is 1 over x. So h prime of t is just 2 times the derivative of the log, which is 1 log t, which is 1 over t. So the answer is 2 over t. So that's all there is to it. And the last differentiation function is capital E of x is e to the minus x squared. And I could think of this as a composite function. This is like e to the g of x, where g of x is minus x squared. Or if you like, f composed with g of x, where f of x is e to the x. So e is a composite function with f and g defined like this. So e prime of x, this is f prime of g of x, g prime of x. F prime is e to the x. The derivative of e to the x is e to the x. And g prime of x, the derivative of minus x squared, is minus 2x. So this is f prime of g of x, that's e to the g of x, or e to the minus x squared, times g prime of x, times minus 2x. Or it looks better if you write it in the opposite order, minus 2x e to the minus x squared. Yeah, that's what it is. Problem 8 is a fundamental problem. So problem 8 is a fundamental problem, problem 6 rather, is a fundamental problem in calculus where you're given a curve and a point on the curve and you want to find the tangent line. So we're looking at the curve y equals x cubed minus 9x. Let's see, we want to graph it. Well, if we can factor this, it makes the graph a little bit easier. I can factor out an x. That's x times x squared minus 9. And x squared minus 9 factors into x plus 3 times x minus 3 times x. So this says if you're looking at the function, so this is my function f of x. And its zeros are at 0 plus or minus 3. I want the tangent at the point x equal to 2. It's nice to know what is the value. So according to this, f of 0, f of 3, and f of minus 3 are 0. And f at 2 is 2 cubed minus 9 times 2. That's 8 minus 18 is minus 10. So this is minus 3, minus 2, minus 1, 0, 1, 2, 3. And let's say this is 5, 10, minus 5, minus 10. The function is 0 at minus 3, 0, and 3. What is it at 1? F of 1 is equal to 1 cubed minus 9 times 1 is minus 8. So at 1, it's minus 8. And at 2, it's minus 10. The f of 1 is minus 8. F of 2 minus 10. And it's odd, so it's the other way around up here. And so somehow, let's see, this function Function is going to have a graph that looks something like this. Right? Because any cubic curve has a graph that goes up, down, and then up. And this is the point 2, comma, minus 10. This is the point on the curve we want to compute the tangent for. So the tangent line at the point on the curve 2 minus 10 has slope. The geometric interpretation or meaning of the derivative is the derivative at a point is the slope of the tangent line there. Has slope f prime evaluated at 2. What is f prime of 2? Let's just note. If f of x is the function x cubed minus 9x, f prime of x is 3x squared minus 9. So f prime of 2 is 3 times 9 minus 9 is 18. So the tangent line going through the point 2 minus 10 has slope 18. Oops.
Why did you choose the 0.2 and 10 and minus 10 specifically?
So the problem is find the equation of the tangent line at x equal 2. So at x equal 2, so this is the graph of this cubic curve. At x equal 2, when x is equal to 2, y is equal to 2 cubed, 8, minus 9 times 2, 18. 8 minus 18 is minus 10. So this is the point on the curve. And when I evaluate, if I do this correctly, let me do it, if I didn't do it correctly, f of x is x cubed minus 9x. That's the function. The derivative is 3x squared minus 9. So when x equal 2, this is 3 times 4 minus 9, which is 12 minus 9, which is equal to 3. So this tangent line has slope 3. So by the point slope formula, right, what does the point slope formula say? The line through the point x1, y1 with slope m is y equals m x minus x1 plus y1. So from pre-calculus or high school, you learned the equation of a straight line through a point with a given slope. So in this case, m, the slope, is equal to 3. x1 is 2, y1 is minus 10. It's the line through the point 2 minus 10 with slope 3. So the tangent line is y equals 3, x minus 2 minus 10, which is 3x minus 16. So this tangent line is y equals 3x minus 16. That's the equation of the tangent line. And you can see when x equals 2, you get minus 10. So this line goes through this point, and the slope is 3. Problem 7 is a refinement of this. In problem 7, we have the function f of x equals x squared minus 4x plus 6. So you know this is a parabola. the graph of every quadratic equation is a parabola. If you want to graph it, let's see, there are lots of ways to graph a parabola. I could say this is x squared minus 4x plus 4 plus 2, because 4 plus 2 is 6. And x squared minus 4x plus 4 is x minus 2 squared plus 2. So one way to see what the graph of this looks like is, if you start with the usual parabola, y equal x squared, if you look at y equals x minus 2 squared, that shifts the graph 2 units to the right. And if you take my function f of x, which is the same as x minus 2 squared plus 2, it takes this parabola and moves it up 2. So the vertex is there at x equal 2. And this parabola looks something like that. Here's the point 2, 2. So that's the graph of my parabola. And we want the tangent lines at x equal 1 and x equal 2. So f of 1 is equal to 3. And if you plug in x equal 3, you also get 3. So here's the point 3, 3. And this is the point 1, 3. And we want to compute the tangent lines at those two places and find where they intersect. Here's one tangent line, here's another tangent line, and there's a certain point this point right here, this is the intersection of the two tangent lines. So how do we find these two tangent lines? Well, to find the tangent line at x equals 3, for the function f of x, f prime of x is 2x minus 4. So this line has slope f prime of 3, which is 2 times 3 minus 4, which is 6 minus 4 is 2. So, oops, just one second. Sorry, so let me continue. So this is going to be the slope of the tangent line of 3. So this line has equation y equals the slope 3 times x minus 3 plus 3, which is 3x minus 6. That's the tangent line at x equals 3. And for the tangent line at x equals 1, it has slope f prime of 1, which is 2 minus 4 is minus 2. So the line has equation y equals, oops, sorry, this is wrong. F prime of 3 is 2. I should have put it, this should be a 2 here. And always good to do these things correctly. 2 times x minus 3 plus 3, which is 2x minus 6 plus 3, 2x minus 3. And when x equals 3, this is 3, so this is okay. This line has slope minus 2, so the equation of the line using the point slope formula is minus 2 times x minus 1 plus 3, which is minus 2x plus 5. So this tangent line is y equals 2x minus 3. this tangent line is y equals minus 2x plus 5. And we have to find the point of intersection. That is, for what value of x does 2x minus 3 equal minus 2x plus 5? That's the same as 4x equals 8, or x equals 2. And when x equals 2, y equals 2. So the point of intersection, let's see, something isn't quite right here. So 2x minus 3 is minus 2x plus 5. 4x equals 8, x equals 2. And on this line, when x equals 2, 2x minus 3 is 4 minus 3 is 1. And on this line also, x equals 2, y equals 1. So the point of intersection is 2, 1. And this is the solution to the problem, 2, 1.
One question, please.
All right.
I want to know f prime x equals 2x minus 4. How did you get that?
So if you have the function x squared minus 4x plus 6, when you differentiate, the derivative of x squared is 2x. The derivative of minus 4x is minus 4. The derivative of 6 is 0. So that's the derivative.
Oh, I thought we're gonna get the prime from x minus 2 squared plus 2. So we
It's the same thing. If you differentiate this, you'll get the same result. This you would differentiate by the chain rule. You would get 2 times x minus 2. 2 times x minus 2 is 2x minus 4. It's exactly the same thing.
Okay, thank you.
Okay. Problem 8 is to use the definition of the derivative to calculate two functions. So this is the definition of the derivative. This is the fundamental definition. F prime of x is the limit, as you can either use h or delta x. I prefer h. The limit as h goes to 0 of f of x plus h minus f of x over h. So we apply this first to the function f of x equals x squared. So in that case, f of x plus h is x plus h squared, which is x squared plus 2xh plus h squared. So f of x plus h minus f of x is x squared plus 2xh plus h squared. That's f of x plus h. Minus f of x, which is x squared. And the x squareds cancel. So you get, sorry, I forgot the h here. You get 2xh plus h squared. And then we're taking this difference and dividing by h. And when you divide by h, see what you have here is, I can factor an h out, h times 2x plus h over h, which is just 2x plus h. So just doing the algebra to calculate this, what is called difference quotient, this whole thing is simplified to be just being 2x plus h. So I take the limit as h goes to 0. And as h goes to 0, we get 2x. So that's the proof that the derivative of x squared is 2x. But this problem says use the definition of the derivative. If you write down f prime of x equal x squared, you get 0 credit because you haven't solved the problem. The problem is to derive that fact from the definition of the derivative. So you have to go through all of this. And in part B, we're looking at the function f of x equals 1 over x. So f of x plus h minus f of x, that's 1 over x plus h minus 1 over x. Excuse me. F of x, 1 over x plus h minus 1 over x. So if you don't know what else to do, you just subtract the fractions. That means you put them over a common denominator of x times x plus h. So you get x minus x plus h. And the x's cancel, you get minus h over x times x plus h. So then if you take the limit as h goes to 0 of f of x plus h minus f of x over h, that's the limit as h goes to 0 of minus h over x times x plus h divided by h. Of course, the h's cancel. You get the limit as x goes to 0 of minus 1 over x times x plus h. And as h goes to 0, this goes to x times x. You get minus 1 over x squared. So that is using the definition of the derivative to compute the derivative of 1 over x. And then the third derivative to calculate is f of x equal sine of x. So f of x plus h is the sine of x plus h. By the addition formula for the sine, this is sine x cosine h plus cosine x sine h. So sine, so f of x plus h minus f of x is the sine of x plus h minus the sine of x. This is the sine of x plus h, sine x cosine h plus cosine x sine h minus sine x. I'll put that here because then I can factor out a sine from this first term. I get sine of x times cosine of h minus 1 plus cosine x times the sine of h. So if I divide by h, f of x plus h minus f of x over h is equal to the sine of x cosine of h minus 1 over h plus cosine x sine h over h. And then if I take the limit as h goes to 0, what do I get? I get sine x times the limit, because this doesn't depend on h, it only depends on x. The limit as h goes to 0, cosine x minus 1 over h, plus cosine x times the limit of sine h over h as h goes to 0. And I already calculated both of these limits. This limit is 0, and this limit is 1. So the answer is cosine x. So that's how we prove, in fact, that the derivative of the sine is equal to the cosine. And then the last problem on the review is elementary rules of motion. A cannonball is shot up into the air with an initial velocity of v naught an initial height of s naught, and its height at time t, s of t, is given by this formula, minus 4.9 t squared plus v naught t plus s naught. So this is given to us. You don't have to derive this. It's an elementary fact from beginning physics, but it's irrelevant. If you shoot a cannonball straight up into the air, starting at a height s naught and the initial velocity v naught, the height at time t is given by this function. So in the problem we're given, it's shot from the ground, so the initial height is 0, and the initial velocity, in whatever units we're measuring, like meters per second, but is 196. What does this graph of this function look like? It's quadratic, which means it's a parabola. The leading coefficient is negative, so the parabola is going to be looking like this. If this is time, and this is the height, this is the function s of t. Right? It's going to go up and come down. And at some point, it has a maximum height. And the maximum occurs when the derivative is 0. Right? When is the derivative 0? The derivative is minus 4.9 times 2t plus, right, maybe I should. So with these values for s naught and v naught, s of t is equal to minus 4.9 t squared plus 196t plus 0. So f prime of t, 4.9 times 2 is 9.8t plus 196. This is actually how fast the cannonball is moving, the derivative of the positions of the velocity. When is this equal to 0? When 9.8t equals 196, or t equals 196 over 9.8. Let's see, 2 times 9.8 is 19.8. So I think this is 20. So 20 seconds after the ball was shot up in the air, it reaches its maximum height. So the maximum height is at s of 20, which is minus 4.9 times 20 squared plus 196 times 20. So we just need to calculate that, minus 4.9 times 400 plus 196 times 20. What is that? 2 times 6 is 2. 2, 8, 2, 9, 18, 19, 392. What is this? This is minus 49 times 40. This is I think 1960. And 3920 minus 1960 is 1960. So if this is right, this is the maximum height. And when does it hit the ground? It hits the ground when the height is 0. So we have the height, s of t, is minus 4.9 t squared plus 196 t. That's equal to t times 196 minus 4.9 t. That's equal 0 when t equals 0, because that's when it's shot up in the air, and when 196 minus 4.9 t equals 0, which means t is 196 over 4.9, which is 1960 over 49. And that, I believe, is exactly 40. So the ball is shot up into the air, and it hits the ground 40 meters away. It gets its maximum height at 20. And the velocity when it hits the ground, the velocity is the derivative of the time. The derivative of the time we already saw is minus 9.8 t plus 196. So S prime at 40 is, let's see, 196 minus 9.8 times 40. That's 196 minus 392, which is minus 196. And why is it negative? Because it's going down. It's decreasing. So that's the whole answer to the problem.